Chromatographic analysis, softening of hard water, the cleansing action of soaps, and purification of water are all surface-mediated chemical processes. In these examples, the reactions occur at the surface. The branch of chemistry that deals with the study of the phenomena that occurs on the surface or interface, that is, at the boundary separating two bulk phases, is known as surface chemistry. An interface is a surface that forms a common boundary between two different phases, such as an insoluble solid and a liquid, two immiscible liquids, or a liquid and an insoluble gas. The two bulk phases refer to the pure compounds or solutions involved in the reaction. The interface is represented by putting a hyphen or slash between the two bulk phases involved. For example, solid-liquid or solid/liquid. Surface chemistry is an important branch of chemistry as a number of phenomena like dissolution, crystallization, corrosion, heterogeneous catalysis, and electrode processes occur at an interface. Let us consider two molecules, one present in the bulk and the other on the surface of the liquid phase. The situation for the molecule on the surface of the liquid is different from the one in the bulk of the liquid. The molecule in the bulk experiences a balanced force of attraction from all directions. However, the molecule on the surface is surrounded by liquid molecules of the same phase and also by fewer molecules from the gaseous phase. As a result, the molecule lying at the surface experiences an unbalanced force or some net inward force of attraction. Similar inward forces of attraction exist at the surface of solids. If you put solid charcoal in a closed vessel containing oxygen, you observe that oxygen molecules are attracted to the solid surface of charcoal. As a result, the concentration of the gas on the surface of the solid increases. The same reaction occurs if a liquid put into a closed vessel containing gas. The gas molecules will accumulate on the surface of the liquid. This phenomenon of attracting and retaining the molecules of a substance on the surface of a solid or liquid, resulting in a higher concentration of the molecules on the surface, is known as adsorption. The substance on the surface of which adsorption takes place is called the adsorbent, while the substance thus adsorbed is called the adsorbate. In the example that we just saw, the molecules of oxygen are the adsorbate, while the solid charcoal is the adsorbent. The reverse process, that is, the removal of the adsorbed substance from the surface, is called desorption. It can be brought about by heating or by reducing the pressure. The adsorption of a gas on the surface of a metal is called occlusion. For example, hydrogen is adsorbed on the surface of nickel or palladium. It is important to note that adsorption is a surface phenomenon. Hence, greater the surface area of the adsorbent, greater is the extent of adsorption. Thus, finely divided metals and substances with porous structure are good adsorbents as they provide large surface area. Charcoal, silica gel, alumina gel, and clay act as excellent adsorbents. Let's look at some examples of adsorption. While clarifying sugar, an aqueous solution of raw sugar is passed over beds of animal charcoal. The animal charcoal absorbs the undesirable colors, and a colorless sugar solution is obtained. When delicate electronic equipment is stored, silica gel is used as a dehumidizer, since it makes the air dry by absorbing the water molecules present in it. Let's look at one more example. Add some activated animal charcoal to a dilute solution of an organic dye, methylene blue. Stir the solution thoroughly and then filter it. You will find that the filtrate thus obtained is colorless. This is due to the adsorption of the dye on the surface of the animal charcoal. It is very important to note that adsorption and absorption are two different phenomena. Let's look at how they are different. The term adsorption refers to the attraction and retention of the molecules of a substance only on the surface of a solid or liquid, while absorption refers to the passing of a substance through the surface into the bulk of a solid or liquid. Adsorption is a surface phenomenon, whereas absorption is a bulk phenomenon, and the substance is uniformly distributed throughout the bulk. Let us understand this difference through an example. If a piece of chalk is dipped in a solution of ink and then broken, it is found that the actual pigment, the ink, is present only on the surface of the chalk and has not moved into the bulk of the solid. However, the solvent in which the pigment was present has uniformly passed into the bulk of the solid. Thus, the color component of the ink has undergone adsorption, while the solvent has been absorbed by the chalk. Another example is the action of water vapor. Water vapor adheres to the surface of silica gel. This is an example of adsorption, since the molecules are retained on the surface of the adsorbent. However, if we place calcium chloride in a closed vessel containing water vapor, calcium chloride absorbs water vapor and forms hydrated calcium chloride. This is an example of absorption, because water passes through the solid surface of calcium chloride. Sometimes, adsorption may be followed by the dissolution of the adsorbate in the adsorbent. This means that first, the material appears on the surface of the adsorbent and then passes into its bulk. When the two processes occur simultaneously, it is known as sorption. Dyeing fiber is an example of sorption. Dyes get absorbed as well as absorbed on cotton fibers. Let us now look at the thermodynamic aspect of adsorption. Adsorption is accompanied by a decrease in the residual forces of the surface. This implies that some energy is released when the molecules of the adsorbate get attracted to the surface of the adsorbent. That is, the change in enthalpy, delta H, is negative for the process. Also, the degree of freedom of the adsorbate decreases upon adsorption, which means that the change in entropy, delta S, is also negative for the process. We know that for any thermodynamic process to be spontaneous, the Gibbs free energy change, delta G, must be negative. The Gibbs equation is delta G is equal to delta H minus T delta S. So, delta G can be negative if delta H is sufficiently negative, since minus T delta S is positive for the process of adsorption. when delta H becomes equal to T delta S, or when delta G becomes 0, the adsorbate and the surface reach a state of dynamic equilibrium.